Okay, so we start this morning session with Baptiste Cercle from Ecole, and he's going to give a talk about W-algebra, Gaussian Free Fields, and Dotsenko-Fateev integrals.
Thank you for the introduction, for the invitation to speak here today. So since the topic of the conference is quite diverse, I will try to discuss some connection between the different notions that we are going to see during this program. And especially today, I would like to discuss some connections between some objects that come either from vertex algebras, like W-algebras, from probability theory, Gaussian free fields, or from I don't know, integrability, like CFT and very classical numerical. So I will try to be as clear as possible and try to explain the connection between the three objects. So I will try to talk to everyone in the room, but if something is not clear, please do not hesitate to interrupt me and ask any question that you feel necessary to ask. So in the first part, I would like to discuss the connection between Gaussian free fields and the Heisenberg vertex algebra, which is somehow a bit classical, but I will try to explain it in the setting of that we are using nowadays to address UV CFT, for instance. So the first object that we want to consider is Gaussian free field. So we'll first introduce this probabilistic setting in which the Gaussian free field appears. So what is the Gaussian free field? The Gaussian free field is somehow a random function. It's not really a function, as we see it. So first question is, how do you define a random function? So say you want to define first a random function which takes values on a circle, S1, and has values in a real one-dimensional Euclidean space here. So a natural way to do that is to expand this function in Fourier modes. So you write that phi ei theta is the sum of some modes phi n times e to the I n theta. And then what you can say to define a random function, you can say that this phi n are assumed to be random. So I assume since this is well valued, I say that phi minus n is a conjugate of phi n. So sampling a random function on a circle somehow is the same as sampling an infinite collection of random variables phi n. And the way I will sample them is very specific. So today I will assume that this phi n will be written in the following way. So I write the real part, imaginary part, in the following way. So what are these xn and yn? Xn and yn are two independent families of independent Gaussian random variable, the usual random variable.
Sorry, what was the last line?
This thing?
Yeah.
It's just saying that it's a Gaussian, like the usual Gaussian random variable. So this means that this mean is 0 and the variance is 1. So, yeah, for instance, I can write something like if I want to compute, so you have a probability measure associated to this, which I call the, so you get a probability measure, which I call like PS1, and you have an expectation that I denote S1. And for instance, if I want to compute expectation of phi n, phi m, with respect to this probability measure. So what is it? It's just, okay, I integrate. I use this parameterization in terms of x and y. So the space of coordinates is F2 times positive integers. So this is for n strictly positive. And then, so phi n is just xn plus or minus depending on the sign, to square root of absolute value of n. Phi m is just xm plus or minus and then the probability measure on this space, like the put on this space, is just product minus xk squared plus square. This is really the definition of my probability measure. And if I want to define the expectation of any functional of this phi n phi m, I will just replace this expression by the function that I want to consider. So this is like you can take this as a definition if you wish.
So here is n different of 0.
Yeah, sorry. Here n is positive.
But in phi.
Here. It's just I will explain later. Like your phi 0, somehow you want to define it as a Gaussian variable with like infinite variance, which is just Lebesgue measure. So I've not explained yet what is this phi 0. So for the moment, I just say that this phi n, from this phi n, using this phi n, I can define a probability measure on S1 on such functions. I have not explained yet what is this phi 0. On here, so this is like a not too difficult computation when you're used to this probabilistic language. This is just 1/2n. And so this is a bit reminiscent of like computational relations in the Heisenberg algebra. This is somehow dual to this. Is this clear? Very well. Of course, you can play the same game. If you want to define a random function which takes values instead of the circle S1, we want to define a function which takes values inside the unit disk. So this is a unit disk. What I can do is I can replace this EIN theta. So X lives inside the disk. By Fourier, I write an expression similar to this, but this time, this mod EIN theta are replaced by this function EN of X, which are EN eigenfunction and B. And then, so this is the analog of this EIN theta. And the analog of this phi n, or this alpha n, which are just Gaussian independent Gaussian variable. And we assume that they are centered, that the expectation is 0. And the variance is just 1/λn, where lambda n is the eigenvalue associated to this eigenfunction. Just say if you want to define a random function inside the disk, what you can do is you first you can expand it in terms of eigenfunctions of the Laplacian with the boundary conditions, just that the modes are chosen to be random. And the randomness is chosen in a very specific way. So actually, when you do this, you have a lot of very nice properties such as conformal invariance. All good, all good?
So alpha n now is 0?
Yeah. Actually, in this picture, you see that this, I can also write it in terms of cosinus instead of EIN theta. So the mode can be chosen to be real. It's just a matter of convention. Like, yeah. And finally, I will use a last Gaussian free field in this talk, which takes values on the Riemann sphere, which is C, to which I add a point at infinity, which has values there. And I can do exactly the same thing. I can take eigenfunction of Laplacian. But actually, there is a simpler way to construct such a field, which is I can decompose the Riemann sphere between the disk, the circle, and something that I will denote see, it's not very complementary circle anyway, on the outside of the disk, in the Riemann sphere. And what I can do is I can say that sampling a random function on the sphere is the same as sampling first a function phi according to this measure. Then inside the disk, I can sample a Dirichlet GFF, to which I add this harmonic extension. On the outside, I add another Dirichlet GFF, but on the complementary of the disk. So I say that I can define the Riemann sphere by saying this is this on the disk, and the complementary where P phi is harmonic extension. So this is all the randomness that I will use, I think, during this talk. Yeah, I think there will be no more randomness apart from this. So basically, the main thing is that you can define a random function on the Riemann sphere by first sampling a random function on the circle, another random function inside the disk. And the way you sample this random function on the circle or inside the disk is really like you just sample some Gaussian random variables and you make some smart linear combination of them. And something that I need to say before moving any further is that for this x, the x that I define here, this xd that I define there on this phi, they are not really functions. Actually, they are generalized functions. So almost surely, this x is not a function, but it's lives in distributional space. Geometric on this. Right? So this means that, for instance, you cannot evaluate it pointwise, which makes things a bit tricky.
H minus 1 is Sobolev.
Sobolev space. So you have a metric you just imagine it's a sphere.
Is this just true on the sphere, or is this true for the circle?
It's true for all of them. Like this XD, also it's in H minus 1 on the disk. And the same for the field phi. So phi is H minus 1 circle. So none of them is a real function. So we say we define random function, but actually we define a random distribution instead. Okay, so this is for probability. Another thing that we use in the probabilistic approach is more functional analysis related, which actually related to the usual setting of CFT, which is that of Hilbert spaces. So there is actually a natural Hilbert space which is attached to this picture, which is just the L2 space associated with probability measure. And this Hilbert space is somehow universal. So I define H S1, which is a Hilbert space, as L2 space. So an element of this Hilbert space is a function of infinitely many variables. So this R is the phi 0. And these are the coordinates phi n. And I equip it with a scalar product. The scalar product is just, so I take an element. So an element of this space is a function of infinitely many variables. Order F, expectation of F of So we modify n in z, g of phi n. So this probability measure takes into account all the modes that are not zero, and for the 0, 1, I integrate respect to the Lebesgue measure. On this Lebesgue measure, it's really like the Gaussian with infinite variance. Like if I take n equals 0 here, I would get a Lebesgue measure. So it's nice to have an inverse space because then you can do some functional like this if you reference. Okay. So is it clear this construction of this inverse space? Actually, this thing will be really close to the Heisenberg. Like this is almost a Fock space. We will explain this. So I have defined several fields. So this one is attached to a field that lives on a sphere. I can also define a Hilbert space when I look at what happens inside the disk. And for this, I will first introduce this space FG, which is the same. I evaluate, so I take as an entry a field which is in H-1. So this is a function, an element of this space is a function of a function, like a generalized function. And then I want this to be finite with respect to the following. So semi-definite, linear, whatever. So 2 phi 0 expectation of f of x restricted to g. G of x. So how do I define it? So I first sample my field x like before. So this x, which is just xd plus p phi under this boundary. So I have actually two copies. So I have one copy that lives inside the disk. I have another copy that lives outside of the disk. And if I want to take a field here and to turn it into a field that is defined inside the disk, I just need to pre-compose by the bar theta. So it's 1 over z bar. So this means that if I look at this field x, d thing on the complementary that are pre-composed with theta, this makes this a function that lives inside the disk. And what is the connection with our initial picture? That you can write this as L2 scalar product with respect to the L2 norm of U0F, U0G, where U0F is just the map that takes phi and splits minus Q phi 0 expectation of F is equal to P phi. This is really like if I want to sample a field under this probability measure, I can first sample a field phi, and then I sample a field inside the disk. This is really what I do here. I decompose just this expectation by first saying I look at I first sample a field on a circle, and then from this field on a circle, I define a new functional that will depend on this field inside the disk. And yeah, I must say that all this was introduced in a paper by Guillermo and Vargas from 2020, the conformal bootstrap paper.
What are the names again? Could you say?
Sorry?
The paper.
Guillermo, Rod Vargas, it's a conformal bootstrap. Theory, I think. You can also look. I've put the second version of my paper. The paper with the same name as the title of the talk. So you can also have a look there. Okay.
Very question. Yeah. The source space D or C or sphere is somehow complex dimension one. Can you?
Yeah.
This kind of thing is generalized to compact Riemann surface.
Yeah. Actually, how do you extend it to complex to any compact Riemann surface?
Yeah.
So the Hilbert space is the same. This HS1 remains the same. It's just then you want to do some gluing axiom like so this you can associate an amplitude, and then you can just glue some surfaces together. I just present the simplest case, like in the case of the disk. But then you can imagine, and with a similar thing, you can actually put some, like for instance, you can define some constant amplitude.
Okay.
So and you can really define it on any geometry. It's just that here I take the sphere because it's like easiest case. But this extends to any geometry. Like if you want to define a GFF, you just actually need the Laplacian.
Yeah.
So you just need some kind of Riemannian structure. And some value.
This setup is something coming from CFT or this kind?
Yeah. So everything here is motivated by CFT. So this is actually this Hilbert space here is used in work by Colin on co-authors in like to prove conformal bootstraps, egal axioms, all this stuff for CFT. Plus, I want to explain today, like this is based on functional analysis on heavy stuff. I will just try to relate this picture to the more algebraic one, like motivated by Vertex Operator. So here there's a subtlety, which is this map is actually not injective, it's just the kernel. So how do you see that? If I take, for instance, the Laplacian, okay, if I am able to make sense of this, then it's not hard to see that U0F is equal to 0. Because this is the harmonic extension, so this Laplacian is 0. This field is centered, so its expectation is 0. So this U0F is 0. So this map is not injective, it has a kernel. So what I can do, so in particular, this is not like a positive definite scalar product. So what I can do is I mod out by the kernel of this map. And I define a Hilbert space, which is this quotient, but I need to complete. And then this gives me another Hilbert space. And this Hilbert space is really dependent on the theory that you put. Like this map U0, if you were to consider UV-CFT, you would change this U0 to something else. So this space HS1, it's universal in some sense. The same for free field theory for UV-CFT. This one will change. And so a result by Guillaume and Vargas is that U0 is unitary. So distance to unitary map between the two Hilbert spaces. This means that you can really identify these two Hilbert spaces. Okay. That's all for probability on the functional analysis. Now we'll do some Vertex algebra. So how do the Heisenberg Vertex algebra appear in this picture? So there is actually you can naturally see a Fock space embedded in this picture. So there is in probability, we have a statement which is called the linear chaos decomposition.
Yeah. And what's about C? How do you define the scalar producer?
C. Actually, it's really like this. It's really like you see it in C.
Yeah, this is what I'm thinking about.
Yeah.
It looks like what I would use in C.
Yeah. So basically, when you take this picture, actually, it's just you have one disk, like usual, and you have it's outside. And so you take an element of this disk, and you pair him with an element that comes from the outside of the disk. So it's really like this defines some observable, some correlation function on the sphere, actually.
So this is the principle of reflection positivity.
Yeah, it's reflection positivity.
When you do your clutching function, I assume you're doing 1 over z bar.
Yeah. Preserve the boundary.
Bothers me, the bar.
Yeah, it's just to preserve the circle, to be identity on the circle.
Information for your inner product.
Yeah, exactly. Yeah. Actually,
It doesn't mess with chiral and anti-chiral.
no, actually, this is one thing which is super nice, which is doesn't mess up with the chiralities. Actually, it's crucial for the chiralities to use this map or not 1 over z. And if I had time, yeah, I'm not sure I will have time to do that. It's almost super late. But actually, you really need this 1 over z bar to get to chiralities. It's because our theory has so here you cannot really distinguish between the 2 chiralities. They're really like mixed together. Yeah, I will explain. I will come to that later. Yeah, actually, the reason why we have 2 chiralities is the following. So this linear chaos decomposition. What is it to say that if I only take the modes which are not 0, this can be realized by first looking at functional of the form phi n1, phi np, and it's m1. So maybe I put bar instead. So I look at linear combination of elements of this form. So I look at this algebraic span. And then I look at just finite linear combination elements of this form. And then I take the inverse space compression with respect to this L2 scalar product. And actually, this means that somehow these polynomials really span almost the entire space.
Does what?
They span the entire space. Actually, why is it related to something that you know? It's because this is a real reminiscence of a Fock space. Actually, I can define a Fock space in this picture. So let me define V, which is embedded in this space, by saying that I look at the algebraic span of maps of the same form. I just twist it a little bit, minus q phi 0. So I look at such maps. And then the question is, why is it a Fock space? So why is it a Fock space? Because you can write it in the following way. So I can write it using creation operators acting on a vacuum. So here it's really an algebraic structure. I forget about stories about convergences. I just look at the finite combination of this. So what are these annihilation creation operators in my probabilistic picture. So first of all, it's not too hard to see what is the vacuum state. I just take all this n to be 0, to be like there is no n. So basically, the vacuum state is just the map which takes phi and splits exponential minus q phi 0. Okay. And then I define the AN as follows. So these are just differential operators. The annihilation operator are just differential operators. The A0 is a bit special because there is this Q that I want to keep. If I want the A0 applied to this vacuum state to be 0, I need to add this term. And for the creation operators, I will have this differential operator, but in addition, I will also create a particle. And so it's not really hard to see that. So these are unbounded operators on my inner space, but they are densely defined on closable, so it's fine. And then I have the commutation relations, which are the one that I guess you know. This is just Heisenberg algebra. Here is phi n, here is it's phi minus n. So you see that if you apply a minus n, so for instance, if I do a minus n applied to the vacuum, what is it? The vacuum is exponential minus q phi 0, so n is positive here for n. For n positive. Here I take n positive. If I apply it to the vacuum, so this differential operator is just nothing, it's just 0. But then I multiply by this. And so this gives me like it's the map which takes phi and gives me I n phi minus n exponential minus q phi 0. It's phi minus n because of the good. It's just that so I have my Hilbert space picture, and in this Hilbert space, I construct a representation of the Heisenberg algebra that I view as differential operators, unbounded operators acting on my Hilbert space. And here this n, so this n bar, it's a multi-index, so it's just a way to say that the sum of this.
It's saying it's a multi.
It's not the same.
It's a different P.
Yeah, it's a L.
Oh.
Yeah, sorry. If you sum n1 up to nl, this gives you P. Yeah, sorry. Okay. Pretty cool. So I have a Fock space in my basic picture. The observation, which I need to do, is that here I've described in terms of the field on the circle, but I can also describe it in terms of the field in the disk. So if I describe it in terms of field in the disk, so I see that this, or maybe I give them a name because it's more expensive. So this I call just something like this. Like I have a multi-index n. I just label this states by otherwise it's different. But I'm saying that in terms of the field in the disk, so in terms of I can use my map U0 to express this in terms of functionals of a field inside the disk. And what I have is that this n is just U0 of differential operator applied to my GFF. Where it is TNX. This is just Tn1x 0 and 1 factorial, Tn Lx 0 and L factorial. On these double dots, these are called weak products. So basically, what are these weak products? So I told you before the JFF is not a smooth function, so I cannot really differentiate it. But what I can do is I can regularize it. So I use a smooth modifier, I turn it into a smooth function, so at scale epsilon. And then when I take the limit as epsilon goes to 0, this expression will turn to diverge. So what I can do is that subtract all these diverging terms, and this will give me this weak product. So there is an easy way to represent this weak product. Is not an easy way, but you can use like Hermite polynomials actually to show this type of expressions. But so the claim is you can represent all the states in your Fock space in terms of some derivatives, something that only depends on the germ, like on the field x in a neighborhood of the origin. So in somehow, this Fock space doesn't really see what happens outside of the origin. All that this Fock space sees is what's happening at 0. So we lose a lot of information. So if I want to add an extra dependence, in another point z that lives inside the disk but which is not 0, what I can do is I consider expression of the form. So I take this differential of evaluated at the point z. But I can also put something evaluated at the origin. On this, okay, I can give it a name. Maybe I can call it with a y, which should be familiar to people doing vertex algebras. So the canonical way to give a meaning to this type of expression is just I take the very same expression and I add an extra dependence on a point which is not 0.
My random function, x is my random function.
Sorry?
X is the random function.
Yeah, x is a random function.
But you, on the disk or on the circle?
In the disk.
In the disk.
So x lives in the disk, phi is on the circle.
Wait, so
But-
x of z and then x of 0, right?
Yeah,
So that two
yeah.
different. Yeah.
So basically my field x is the sum of xd plus p phi. Like, so it depends on the phi. So x depends on phi, but it's a function inside the disk. And so it depends on actually every point, all the points in the disk.
You said it's a distribution of the function.
It's a generalized function. So. But it depends on all the points in the disk. And if I restrict myself to the Fock space, I just see what happens in the neighborhood of the origin. So I lose a lot of information. And if I want to add some more information by keeping track of what happens at another location in the disk, naturally I want to look at this kind of expression. And the question now is, what is the meaning of this kind of expression?
So I'm not quite so if I understand everything at the origin, Yep. And basically I know all the phi ends, and I can sum all the phi ends again, and I recover my fields.
Yeah. But so there's something here which is, where you can get more information is when, for instance, when you take this z goes to 0, then actually you can get some more information when you do that. So
So this relates to the regular vertex operator,
exactly.
but I would normally say that there's a state field correspondence, and so you don't lose information because along with the states you have the field.
Yeah, okay, so you don't lose information, but actually doing that you will gain a lot of information. Like for me, it's more you get some combinatorial arguments, some combinatorial facts.
So it's just a tool to simplify something. It doesn't really give you new information because you're told that this span it's a dense subset inside, so it should be enough.
Yeah, that's true. That's true.
But it's
that's
just
enough.
simpler to work with these things as well.
It's just that if you work with this, actually you can make sense of like OPEs, all the axioms that you have in vertex algebras. Yeah. So, yeah, exactly. So if you want to make sense of vertex operators in our setting, this is what you want to do. But I agree that in principle, you don't have much more information. Like everything is already contained in the initial space. But actually, we see this will have some strong consequences. We'll see maybe another day. But okay, so we define this formally speaking. So the question is, what is the meaning of this expression? So you can actually think of this yn of z as a like unbounded operator. If you want to do some function analysis, you can view them as unbounded operators acting on some dense subspace of Hilbert space. But actually, here I want to make the connection with vertex algebras. So if I look at this kind of expression, so for probabilists, I can do Gaussian integration by parts. So by Gaussian integration by parts, I think that this expression it's actually a Laurent series in Z. So the positive modes, for instance, will be given by the 5. The negative one will be given by the derivative of the green function that you get when you do the integration by parts. And so this hints toward the fact that this object, you may want to do it actually not as an unbounded operator, but more as a formal power series in Z minus 1, whose coefficients are endomorphisms acting on my Fock space. So I want to define an object like this. So how do I define such an object? So I will introduce the analog of the GFF in this VOS setting by putting phi of z, which is C plus I of z. This is where I need the two varieties. So A of z is just A0 log z minus some and this A tilde, it's a copy of my Heisenberg algebra where I replace the phi n by the conjugate. And these are two commuting copies of the Heisenberg algebra. So you see that I have at the same time the two varieties. Something depends on z, something depends on z bar. And when I do my transformation, theta is 1 over z bar, actually I see that what I will get is exactly the change. Maybe I can say that if you do this phi on theta plus 2q log prime, I think, I never quite remember. Then this is just the Hermitian conjugate of phi. it's more appropriate meaning. Okay, I'm not sure about the coefficient, but this is like the usual transformation rule for the GFF. Like when you change x, the QGFF changes in such a way. I'm not really sure about the coefficients. Maybe it's
18.
but yeah, there is maybe a minus 1, maybe a 4, maybe 1/2. Anyway.
And what is V? I missed
V is my Fock space.
V is your Fock space.
Yeah, so RE is just a linear operator on my Fock space with some assumptions.
What is 18?
80 it's an independent copy of my AN. So basically, it's the same thing where I replace this A0 by, actually A0 is the same. I replace this AN by some AN tilde, which are defined like the AN, but you change the phi n to their conjugate. And the two copies commute. And you change the Z into Z bar. So you really have the two varieties which are mixed together.
Wait, sorry. So Q is what is Q again?
Q, it's
It's a center
it's
chart or
in
something.
my
That Q, right?
A0 is a d phi 0 plus Q.
Okay. Okay.
My vacuum depends on this Q.
Now, what is the constant term in the phi? Is
But
it
it's a C, like the same C.
just some
C.
constant?
So Q is related to central charge.
Q is related to the central charge. The central charge is yes, sorry, I forgot to say that. Central charge is 1 plus C Q squared.
But C is not the same as C there.
No, so central charge. Central charge. Si, central charge. It's a worse notation as well. But yeah, it's not the same thing. And so if I define this phi, what I have is then from this phi, and this is just an aparté, I can define this vertex operator by saying that I look at derivatives of this formal series that are in normal order. So this double dot, this time it's not weak product, it's normal ordering. Which means that I put the annihilation operator first. The equation 1 last. And then this is, so this n are positive. So here there is no log anymore. It's really a formal series in z on by z minus 1. And you see that this thing is actually, if I define this field in this formal series in such a way, then I recover exactly what I wrote here. So maybe the thing which is quite amazing, at least that I found amazing, is that if this file is really playing the same role as my GFF. It's equal to 0 of the same thing, but I replace the phi by the GFF. And you see that honestly, it's things that are really well done. Like the double dots are really like the same, also the same. But in this, on this side, it's normal ordering. On this side, it's weak products. Okay, so I think that's a very cool thing. So here, let me see. So
I interrupt you for a minute.
sorry.
I thought that U zero of that supposed to act on M bar or M underscore. I don't know. I'm confused. So why? Wait, hold on. So what's happening? Yeah. So that one. So you act on the vacuum instead of act on M underscore. It's like the one on the left-hand side
This one?
equation. Yeah.
I act on a vacuum, yeah.
It's act on the vacuum, not
Yeah.
M underscore, right?
Not in.
Because like on the
No,
other
you
one-
act on the vacuum. Yeah, you act on the vacuum. This one.
Oh, okay, okay.
Yeah.
Alright.
So you act on the vacuum. So what you get is just this state M bar.
Ah, I see. Okay, gotcha.
So this is something I can.
No, that's good. That's good.
So okay, you have this identification, which is quite amazing. And now there is a choice. I can move to W-algebras on Gaussian-Fateev integral, which was the title of the talk. Or I can spend more time trying to explain the correspondence between probability and vertex operator algebras. For example, explain what is the meaning, why the VOA actions are natural in this setting. So I guess you tell me if you have a preference. We can make a vote. So I can spend more time explaining discussing the correspondence between the two, or I can just move to W-algebras on Gaussian-Fateev integrals. One W-algebra. Okay.
I got the picture. Good enough.
Okay, W-algebras. So now I have a probabilistic construction of the Heisenberg vertex algebra. So maybe the first step is I can consider like there is an easy generalization of this. So now I consider my field on all the GFL that I've considered through this tree to take value still on the circle, but this time they have values in a higher dimensional Euclidean space. So this R to the R, so basically you view it as a subset of C to the R, which you should think of as a Cartan superalgebra of some algebra G. I will come to that later. So now I generalize the previous correspondence to get a probabilistic representation higher rank, sorry. So basically, what you can do is you just sample some copies, independent copies. Okay, but first, what I claim is that I can generalize this to a higher rank Heisenberg algebra, which is, I guess, not too difficult to imagine. And then something that I didn't talk about. Maybe there's something else before that. Oh yeah. Something that I didn't talk about was some very special operators which are called bosonic vertex operators. What are these bosonic vertex operators? They are the analog of the vertex operator that we have in UV onto the CFT. So in UV onto the CFT, you define this V alpha of Z, which are just exponential alpha x of Z, where alpha is in R to the R and Z is inside the disk. If I use this correspondence, I can also define the very same object on the VOA side, which I denote in calligraphic way, which is exponential of alpha this time, on which I normal order. And here's alpha on the same. So this one has two corollaries, but I can define one with only one corollary by saying I keep only the holomorphic part. Or the dependence on not part. you recall that this was a sum with an z to the minus n. So the effect of this bosonic vertex operators is the same as Girsanov for probabilist. So when you act on for suitable f, so for x that depends only so if you evaluate the field inside the disk of radius z, norm of z, then what you have is that this bosonic operator, they act as u0f is, we first have the term in P5. And then you have u0, but you have shifted your u0. Does not depend on x, but rather on x plus alpha green function z. So you add a log singularity. So JD is a green function. So for probabilists, this is nothing but Girsanov. And this kind of statement, you can prove it like doing good computations. Yeah. And actually, you can prove a similar statement with the bosonic vertex operators. So when you just add a plus, so you keep only the holomorphic part, and here you have the holomorphic part of the green function that you view as a homoconverse series. And from this bosonic vertex operator, you can form something which is called screening operator, which are just contour integral b alpha plus of z. So you take this operator. It's so you know the green function. It's a log of 1z w bar z minus w. So it depends on the modulus squared. You remove. Yeah. You remove the modulus.
But this is multi-valuable.
Yeah. So this is why you know this statement I didn't say something too precise like you need to consider special functional f for this to make sense. Yeah. Then you can define string operators. This bosonic vertex operators. So you just keep. So here you can actually you can show not to it's not too complicated to show that this is well defined over V. When you act on V, it's not too difficult to show it's well defined. When it sends V to another Heisenberg module. And then you can define the set W. Okay, so we have all these bosonic vertex operators on these string operators.
What is the contour you take?
It's just any contour surrounding the origin. So basically, you just keep, so this you expand in the one of z. So you just keep the 0, minus 1, 1, the minus 1. So this is formal, but actually, when you apply it to an element of your Fock space, this thing will really be like a long series. Yeah,
But it reduces to finite sum, no?
Finite, but at least in one direction, it's finite. So the coefficients are well defined because you have the exponential. But so you can really make sense of these string operators. And then where do the algebra arrive? The algebra arrives. So assume now that you are given a special basis of R to the R. So I'm given some EI, basis of R, such that this normalized scalar product is given by the Cartan matrix of G, where G is some simple complex algebra, like so make this assumption, like take any elements, any basis of R to the R, which satisfies this this condition. And then define the subspace of your initial Fock space by looking at the intersection of the kernel of this string operator, but where you take the alphas to be very specific. You assume them to be proportional to these simple roots, to this basis. So gamma is in 0, 0, 2. Yeah, so this I are simple roots of pure algebra. Then it's a theorem by Fegin, I think, first Fegin Frankel. I was not born. So theorem by Fegin Frankel is that integral function and function roots. So for generic gamma, so gamma outside the dense open subset, or in a dense open subset of 0 to 2. So the data of this WG, it defines the vertex algebra. So WG with the vacuum, the translation, and the vertex. So this, you view it as a subalgebra of the Heisenberg algebra. This defines vertex algebra. Okay, that's not the big part in the statement. The big part is that this WG, actually, it's generated by some programs. So I think I'm a bit over time, as usual. No?
Oh, we started 10 minutes late, so more or less 1 hour now.
Yeah, so I just conclude that, I think. So the statement is that this, so the way you can generate this space is this is not exactly the statement of Fegin Frankel, but this is adapted in our context. So you can generate this space. So these are Young diagrams. With entries bigger than SI. These SI are called, rather SI minus 1 are called exponents of the Lie algebra. And this W, so W minus lambda I SI. Well, these are like differential operators, mostly differential operators. Multilinear, I don't know to call them. Maybe a simple example that if you take the rank to be equal to 1, which is the one that we investigated before, you have only one sum over one Young diagram. This diagram, its entries are greater than 2. So in the case A equal 2, in case A equal 1, you have a span of L minus lambda 1, L minus lambda L vacuum, where lambda L is greater than 2. And this L minus N is just the usual Virasoro. So it's just to say like you have some differential operators in X. In one case you have this. In general, you have something which is more complicated on your algebra. So the final message is just that you can represent your W-algebra using differential operators acting on your field X. And so this gives a way to take results from like W-algebras, representations of W-algebras into statements in probability. For instance, one application of this correspondence is to prove some one entities for correlation functions. Like for instance, prove the one entities for Gaussian-Free Fields integrals. Hopefully, at some point, it will give one entities for CFTs in general. The thing is, of course, these currents are absolutely not explicit in general. We don't know how to compute them. So seeing that you have one entities without having an explicit expression for them, I think it's quite nice. I think it's great to talk about this. Sorry.
Thank you very much. Maybe one quick question, and we can. There's a coffee break.
With a coffee break, we can shift, restart it in 11:11.
Maybe one question. If someone wants this question, otherwise we can ask also in the coffee break. Maybe I have one question. So this is for the free field, what you explained?
Yeah.
But it's possible to do for a non-trivial CFT.
Yeah. Actually, the Gaussian-Free integral is non-trivial because you break the Heisenberg symmetry, but you still keep the W symmetry. Actually, the identity that you use to say that you keep the W symmetry, basically, it's like combinatorial identities that you can, I guess, use to prove a similar statement for total CFTs. For me, it would be a way to prove that you have this W symmetry for total CFT, which are more complicated.
Why do you have this restriction on gamma?
It's just for the sake of presentation. Like there is no.
Because the theorem doesn't need any restriction.
No, there is no restriction. Actually, it's just for the sake of the presentation. Actually, in this picture, you can take everything is algebraic as long as you forget about the Hilbert space structure, the scalar product, etc. Then you can take anything like this Q to be complex, some structure should be complex.
Okay, so let's thank Baptiste again, and we have a 15 minutes break.